What if the key to the next leap in human progress lies not on Earth, but in the vastness of space, where autonomous robots are already preparing to mine the moon and beyond? This might sound like a plot straight from a science fiction novel, but it's becoming a reality faster than you might think. Imagine the possibilities: an economy fueled by the resources of asteroids, a world where shortages of rare minerals are a thing of the past. These autonomous mining robots are at the cutting edge of technology, transforming our approach to resource extraction. In today's exploration, we uncover how these intelligent machines might redefine our capabilities, tackle the immense challenges of space, and set the stage for a future where humanity reaches further than ever before. Fasten your seatbelts as we journey into this revolutionary frontier of extraterrestrial mining. To fully appreciate the technological marvel of today's autonomous mining robots, let's embark on a journey through the evolution of mining technologies. Mining, one of humanity's oldest and most vital activities, has transformed dramatically over the years, evolving from manual labor and mechanized tools to the sophisticated, self-sufficient robots we see today. This transition marks more than just the automation of a traditional industry. It heralds the dawn of a new era of mining innovation. In the early days, mining was largely a manual endeavor. Workers relied on simple hand tools and physical labor to extract minerals from the earth. As industrialization gained momentum, mechanized tools like drills and steam-powered engines revolutionized the process, increasing efficiency and safety. Yet, as the demand for minerals grew with the technological boom of the 20th century, so did the challenges of extraction, pushing the need for more advanced technologies. The real turning point came with the advent of digital technology and the development of robotics. By the late 20th century, remote-controlled machinery was introduced into mining operations. These machines could be operated from a safe distance, reducing the risks faced by miners and allowing operations in hazardous environments. The integration of global positioning system technology and sensors began to provide real-time data, enhancing precision and control. The 21st century witnessed the incorporation of artificial intelligence, fundamentally changing the mining landscape. AI integration facilitated predictive maintenance, real-time decision-making, and autonomous navigation. These AI systems allowed machines to learn from their environment, adapting to new challenges and optimizing performance without human intervention. This level of autonomy was crucial as we began contemplating mining ventures beyond Earth. The leap toward extraterrestrial mining necessitated another wave of innovation. The harsh and unpredictable environments of space and the moon posed unique challenges that terrestrial technologies could not solve. Engineers developed robots capable of operating in low-gravity environments, equipped with sophisticated AI to navigate and extract resources autonomously. These robots are designed to withstand extreme temperatures and radiation, using solar energy to power their operations, an essential feature for sustainability in space. Remote control systems have also been a game-changer, with Earth-based operators able to control these robots, albeit with a communication delay. We can safely explore and mine areas that were previously inaccessible. The synergy between AI-driven autonomy and human oversight ensures these robots can adapt to unforeseen conditions while maintaining a reliable support system. Consider the robotic landers and rovers that have already been part of successful missions to the Moon and Mars. Their ability to collect and analyze samples has provided invaluable data, paving the way for future mining missions. These missions showcase how the lessons learned from past technological advancements have been applied to create robust machines capable of autonomous extraterrestrial extraction. As we continue to innovate, the line between traditional mining and space mining blurs, with technologies from each domain feeding into the other. The advancements in AI, robotics, and remote operation technologies not only redefine what's possible in mining, but also extend the reach of human industry into the cosmos. This ongoing evolution of mining technologies promises to unlock new resources, support future space exploration endeavors, and maybe, just maybe, offer solutions to resource scarcity on Earth. By understanding the remarkable journey of mining technologies, we can better appreciate the unprecedented possibilities that autonomous mining robots bring to the table. They're not just machines, they represent a profound shift in how we interact with the world and beyond. As we look to the stars, these robots will be our pioneers, transforming untapped celestial bodies into the mines of tomorrow. At the heart of autonomous mining, robots lies a synergy of cutting-edge technologies, each playing a pivotal role in empowering these machines to operate with minimal human intervention in some of the harshest environments known to existence. To appreciate the science behind these marvels of modern engineering, it's essential to delve into the core technologies that enable their autonomy, ensuring they can adapt and thrive on the moon and beyond. One of the fundamental components of these robots is artificial intelligence, a technology that enables machines to perform complex tasks by mimicking human cognitive functions. AI isn't just about mimicking human thought processes, it involves creating systems that can learn and adapt autonomously. This is where machine learning comes into play. Machine learning allows these robots to identify patterns and improve their decision-making abilities over time based on the data they gather. For instance, when faced with new and unexpected challenges on the lunar surface, these robots can draw from previous experiences to determine the best course of action, much like an experienced miner would back on Earth. Complementing AI is computer vision, a specialized field of AI that equips the robots with the ability to interpret and understand visual information from their environment. This technology is crucial for navigation and obstacle detection. In the absence of well-lit and clearly marked paths on the moon, these robots use cameras and sensors to create real-time, three-dimensional maps of their surroundings. This mapping allows them to identify craters, rocks, and other potential hazards, enabling them to navigate safely and efficiently. Computer vision also aids in identifying the precise locations of valuable minerals and resources, ensuring that their extraction efforts are targeted and effective. Advanced sensors are another critical technology at play. These sensors range from infrared cameras to spectrometers, each designed to gather different types of data. For example, infrared cameras help detect temperature variations, which can indicate the presence of certain minerals. Spectrometers analyze the composition of materials by measuring the light spectrum. This suite of sensors enables the robots to conduct preliminary analyses of the mining site, ensuring that each scoop of lunar soil is rich with the resources they seek. To function in the extreme conditions of space, these robots are also equipped with robust hardware and energy solutions. Solar panels are a common choice for powering these machines, providing a sustainable energy source that allows them to operate during the lunar day. Their construction materials are chosen for durability to withstand temperature swings that can range from scalding heat to frigid cold. The layered insulation not only protects their internal components, but also maintains operational efficiency regardless of the harsh environment. Communication systems form yet another vital part of the technology landscape. These systems allow robots to communicate with each other and relay critical data back to Earth. Given the distance from Earth, communication is not instantaneous. Yet these systems are designed to manage these delays without compromising the robot's operations. Using algorithms, the robots can make localized decisions autonomously, while strategic guidance and updates are transmitted from Earth-based command centers. In summary, the science behind autonomous mining robots is a fusion of AI, machine learning, computer vision, and advanced sensor technology, all orchestrated to perform seamlessly in space. These technologies work in concert to transform lunar and asteroid surfaces into accessible and manageable mining sites. Each advancement in autonomy not only represents a step forward in technology, but also brings humanity closer to a future where space is not just an empty void, but a realm rich with possibilities. As we look to the stars, these robots are not mere tools, but are increasingly becoming independent explorers, expanding the horizons of what is possible for mining beyond Earth. As we gaze toward the cosmos, pondering the promise of autonomous mining robots, a critical question emerges. What exactly are we mining for on the Moon and asteroids? The answer holds not just technological marvel but economic significance, creating a bridge between our earthly needs and extraterrestrial bounty. Among the most prized resources we're targeting are rare earth metals, water, and the enigmatic Helium-III, each valuable for unique reasons that extend far beyond mere collection. Let's start with rare earth metals. These are critical components in modern electronics and green technologies. From smartphones to electric vehicles, rare earth metals are integral, yet their mining on Earth is fraught with environmental challenges and geopolitical tensions due to their uneven distribution. This is where the Moon and asteroids come into play, potentially offering a sustainable and diversified supply source. Imagine a future where the constraints of Earth-bound availability are lifted, allowing for a boom in technological innovation and development without the ecological and socio-political costs associated with current mining practices. Water, another target, might seem abundant on Earth, but its presence in space holds unparalleled significance. Water on the Moon, primarily found in the form of ice within shadowed craters, is a vital resource for sustaining future lunar bases and missions. More importantly, water can be split into hydrogen and oxygen, not only providing life support but also serving as rocket fuel. This capability transforms the Moon into a strategic refueling station for deep space exploration, enabling missions to Mars and beyond with greater ease and reduced cost. The potential for in situ resource utilization represents a fundamental shift in how we approach space travel, moving from carrying everything we need from Earth to leveraging space's natural resources. Then there's Helium-III, a resource that has captured the imagination of scientists and futurists alike. Unlike its counterparts on Earth, Helium-III is sparse but offers an intriguing possibility as a clean and potent fuel source for nuclear fusion. The Moon's surface holds vast quantities of Helium-III, deposited by solar winds over millennia. Fusion power using Helium-III could lead to a new era of energy production, one where power is plentiful and lacking the radioactive waste associated with current nuclear fission processes. While practical fusion energy remains a dream, the potential of Helium-III could spur a race for lunar dominance, providing a robust incentive for both public and private entities to invest in these mining ventures. But why are these resources so crucial? The global demand for smart technologies and clean energy solutions continues to rise. As emerging economies develop and the global population grows, the need for sustainable and efficient resource management becomes imperative. Mining these extraterrestrial bodies could alleviate some pressures on terrestrial resources, contributing to a more balanced and sustainable global economy. Furthermore, these resource targets underscore the strategic nature of space exploration. By establishing mining operations on the Moon and asteroids, humanity isn't just extending a technological frontier, it's creating a new economic ecosystem. This venture not only promises innovation and sustainability, but also offers geopolitical advantages, positioning those who master these resources at the forefront of future economic and scientific developments. In this light, the autonomous mining endeavors are not merely technological novelties. They represent an economic necessity. By tapping into the Moon and asteroids' vast potential, we unlock new opportunities for growth and exploration that could redefine our industrial landscape, space travel paradigms, and even our understanding of sustainability. As we continue to transition from a planet-bound society to a truly spacefaring civilization, these resource targets and their applications are set to play pivotal roles in shaping the trajectory of human progress. Mining in extraterrestrial environments is not as straightforward as deploying machines and letting them loose on the Moon or asteroids. Despite the promise these autonomous mining robots hold, they must first overcome a series of formidable challenges posed by the harsh environments they operate in. From extreme temperatures and unpredictable radiation levels to the effects of low gravity, each obstacle demands innovative solutions to ensure the success and longevity of these mining missions. Consider the temperature variations on the Moon, which can be drastically different from the conditions we're accustomed to on Earth. Lunar temperatures can swing from a searing 260 degrees Fahrenheit during the day to a bone-chilling minus 280 degrees Fahrenheit at night. Such extremes can wreak havoc on machinery, causing metals to expand, contract, and potentially fail. To tackle this, engineers have designed thermal control systems that protect the robot's internal components. These systems often use a combination of insulation materials, reflective coatings, and heaters or coolers to maintain stable operating temperatures, ensuring that the robots can function efficiently regardless of the time of day. Radiation presents another formidable challenge. Space is awash with high-energy particles from the sun and cosmic rays, creating an environment that can severely damage sensitive electronics. Here, the solution lies in the development of radiation-hardened electronics. These specially designed circuits are capable of resisting the harmful effects of radiation, preventing data corruption and system malfunctions that could jeopardize entire missions. Engineers are also exploring the use of shielding materials, such as layers of lead or other dense substances, to further protect critical components from radiation exposure. Low gravity, a condition present on the Moon and asteroids, affects everything from the movement and stability of the robots to the efficiency of resource extraction processes. In a low-gravity environment, traditional mining techniques that rely on weight and pressure become ineffective. Researchers are developing advanced mobility systems, such as spider-like legs or hopping mechanisms, that allow robots to navigate these terrains without relying on conventional wheels or tracks. Moreover, innovative anchoring systems are necessary to ensure that the robots remain stable while performing excavation tasks, preventing them from inadvertently pushing themselves off the surface. The absence of an atmosphere poses additional issues, particularly concerning dust. Lunar dust is incredibly fine and abrasive, capable of infiltrating machinery and causing wear over time. To counter this, robotics engineers are implementing sealed designs to prevent dust ingress and exploring materials that can withstand abrasion without degrading. Self-cleaning mechanisms, often inspired by nature, are also being considered, helping robots shake off dust buildup that could impede their sensors or solar panels. Then there's the matter of wear and tear. The long-duration missions planned for these robots mean they must be able to operate autonomously for extended periods with minimal human intervention. This necessitates the use of self-repairing mechanisms. Imagine a robot capable of detecting a malfunction in its own systems, diagnosing the problem, and using built-in tools to perform repairs. These mechanisms might involve the use of spare parts carried by the robots themselves, or the ability to reconfigure existing components to compensate for damage, ensuring that operations can continue uninterrupted. Each of these challenges has spurred innovation, pushing boundaries and leading to technological advances that benefit not only space exploration but terrestrial applications as well. The solutions being developed for extraterrestrial mining are poised to make machinery more resilient, efficient, and capable of handling extreme conditions here on Earth. As we continue to refine these technologies, our capability to mine the vast resources of space only grows stronger, promising exciting developments for both the future of space exploration and our resource management on Earth. While autonomous mining robots may be technological marvels, their successful deployment and operation on the Moon and beyond hinge significantly on international collaboration. As we look to unlock the vast potential of extraterrestrial resources, this emerging frontier demands not only technological innovation but also a concerted global effort. Today, more than ever, countries and private enterprises are realizing that cooperative strategies are essential to the success of these ambitious ventures. Let's delve into how international collaboration is shaping this new era of space resource exploration and the regulatory frameworks that guide it. At the core of this collaboration are international agreements which establish guidelines and ensure that activities in space are conducted peacefully and responsibly. The Outer Space Treaty of 1967 remains a foundational document signed by over 100 countries. It sets the stage for how nations should engage in space, emphasizing that space exploration is a domain for the benefit of all humankind. This treaty underscores the necessity of cooperation and mutual respect in pursuing extraterrestrial mining, ensuring that it doesn't become a source of conflict but rather an opportunity for shared advancement. Beyond treaties, we see burgeoning partnerships between national space agencies and private companies. These collaborations are crucial as they combine the expertise, resources, and innovation of both sectors. For instance, NASA Artemis program includes participation from international partners like the European Space Agency, which provides vital components for lunar missions. Likewise, private companies like SpaceX and Blue Origin are working alongside government bodies to develop the technology and infrastructure needed for space travel and resource extraction. These partnerships extend to a myriad of collaborative projects aimed at fostering technological innovation and sharing knowledge. Countries with more advanced space programs often partner with those in the early stages of their space endeavors, facilitating technology transfer and capacity building. Such collaborations not only help bridge the technological gap between nations, but also create a diversified talent pool, enriching the collective expertise in space exploration. For private enterprises, international collaboration offers access to broader markets and investment opportunities. It encourages the sharing of risks and rewards associated with space mining ventures. Companies like Planetary Resources and Astrobotic Technology are exploring joint ventures with international firms, leveraging global expertise to tackle the complex challenges of space mining. This collaborative spirit not only accelerates technological advancement, but also promotes economic benefits on a global scale. Regulatory frameworks are another key element ensuring that international collaboration proceeds smoothly. Organizations such as the United Nations Committee on the Peaceful Uses of Outer Space work tirelessly to develop policies that support sustainable space exploration activities. These frameworks aim to provide clarity on issues such as resource ownership, environmental impact, and the equitable distribution of benefits. By navigating these complex regulatory landscapes collaboratively, countries and companies can ensure that extraterrestrial mining progresses in a way that is ethical and sustainable. Additionally, the Artemis Accords, an initiative led by NASA, seeks to establish a common set of principles grounded in the Outer Space Treaty to guide the civil exploration and use of the Moon, Mars, and other celestial bodies. These accords encourage transparency, interoperability, and peaceful exploration, recognizing that no single nation can claim sovereignty over celestial resources. They open the door for countries to engage in space exploration in a way that respects the interests and contributions of all participating partners. Understanding the global landscape of collaborative efforts in autonomous mining is essential. It highlights not only the technical challenges but the diplomatic and ethical considerations that must be addressed to make space mining a reality. By fostering a spirit of international cooperation, we ensure that the exploration and utilization of extraterrestrial resources align with the shared values of our global community, paving the way for a future where space becomes a realm of opportunity and prosperity for all. As we venture into this new frontier, it is the combined endeavors of nations and enterprises that will ultimately make the dream of space resource mining a reality, benefiting humanity as a whole. Turning our gaze to the horizon, the prospect of mining operations on the Moon and asteroids raises intriguing possibilities that could reshape our economic and environmental landscape. The potential influx of previously inaccessible resources offers the promise of transforming industries and creating new markets. At the same time, this venture demands a careful balance between harnessing these opportunities and addressing ethical and environmental concerns that come with mining in outer space. To begin with, let's explore the economic benefits that lunar and asteroid mining could offer. The extraction of rare earth elements, precious metals, and other resources from space has the potential to revolutionize several industries. For instance, the availability of materials like platinum group metals in asteroids could significantly reduce the costs of manufacturing high-tech devices, electric cars, and renewable energy technologies. By diversifying the supply sources of these critical materials, we could alleviate the geopolitical tensions and supply chain vulnerabilities that currently plague global markets. Moreover, sourcing resources from space could catalyze entirely new markets. Consider the burgeoning field of space-based manufacturing. By utilizing materials directly sourced from the Moon or asteroids, space factories could produce components without the need to launch them from Earth, dramatically reducing production costs and expanding the space economy. This shift could lead to innovations in satellite construction, space tourism infrastructure, and even the development of space habitats, stimulating economic growth both on Earth and beyond. The implications for global economic power are profound as well. Countries and organizations leading the charge in space mining could potentially alter the balance of economic power. Those with the technological capability and resources to establish successful mining operations in space might gain significant leverage in global markets. This could lead to a re-evaluation of global partnerships and influence, presenting opportunities for new alliances and economic frameworks. However, these opportunities are not without environmental and ethical considerations. The challenges of ensuring sustainable practices in an environment as delicate as space are immense. Unchecked mining activities could lead to space debris issues, potentially posing a hazard to both current and future space missions. Moreover, the extraction processes, if not carefully managed, could disrupt the pristine surfaces of celestial bodies, impacting future scientific exploration and research. To mitigate these impacts, several strategies need to be implemented. Firstly, mining operations must adhere to stringent international environmental standards designed to minimize harm. This includes the use of advanced robotics and AI technologies that ensure precision in extraction activities, reducing waste and minimizing disruption to the surfaces being mined. Developing closed-loop systems for resource extraction could help minimize the generation of space debris. Ethical considerations are no less important. The legal frameworks governing space mining must be developed collaboratively, ensuring fair and equitable distribution of the benefits derived from these resources. Furthermore, transparent and inclusive dialogue among international stakeholders can help navigate the complexities of space resource ownership and utilization. In conclusion, while the economic potential of lunar and asteroid mining is considerable, the environmental and ethical challenges must not be overlooked. By investing in sustainable mining technologies and fostering international cooperation, we can pave the way for a future where space resources contribute positively to global prosperity without compromising the integrity of our solar system's natural environment. As we step boldly into this new era of exploration, it is imperative that we do so with foresight, responsibility, and a commitment to the sustainable and equitable advancement of all humanity. The journey is as much about what we gain economically as it is about how we choose to grow as a global community in respecting the new frontiers we venture into. As we stand at the threshold of a new era in space exploration, the potential of space mining is evolving with remarkable speed, driven by cutting-edge innovations and emerging trends that promise to redefine the boundaries of what's possible. At the heart of this transformative journey are advancements in robotic technology and artificial intelligence, each playing a crucial role in meeting the unique challenges posed by extraterrestrial environments. One of the most exciting innovations is the development of self-repairing robots. In space where human intervention is limited and costly, self-sustaining systems are vital. These robots are equipped with the ability to diagnose mechanical issues and perform minor repairs autonomously. Drawing inspiration from biological systems, engineers are developing materials that can heal themselves when damaged, ensuring that robotic explorers remain operational despite the harsh conditions they encounter. This capability is a game-changer, vastly extending the lifespan and effectiveness of mining robots deployed on the Moon or asteroids. Artificial intelligence continues to advance at a breakneck pace, offering sophisticated problem-solving capabilities essential for navigating and extracting resources in unpredictable space environments. Machine learning algorithms now enable robots to analyze large volumes of data quickly, making autonomous decisions about the best mining sites and methods. These improvements allow for greater precision in resource extraction, reducing waste and optimizing operations. Imagine robots that can not only navigate challenging terrain, but also learn and adapt based on the geological data they collect, honing their techniques with each new mission. In addition, the integration of advanced sensor technology is facilitating unprecedented levels of efficiency and safety. Sensors that can detect the composition of minerals in real time enable more targeted mining efforts, ensuring that robots focus only on areas rich with valuable resources. This approach enhances the sustainability of mining operations as it minimizes unnecessary extraction and preserves the integrity of celestial bodies. Another trend to watch is the development of in situ resource utilization technologies. These systems enable us to make use of the resources found on site, such as transforming lunar ice into drinkable water or breathable oxygen, or converting moon and asteroid materials into construction elements. The ability to utilize local resources reduces the need to transport materials from Earth, lowering costs and supporting longer, more sustainable missions. This innovation is key to building permanent facilities on the Moon, which could serve as bases for deeper space exploration. The propulsion methods for transporting resources back to Earth are also undergoing significant advancements. New propulsion technologies such as ion and nuclear thermal propulsion are being developed to offer efficient and reliable ways to shuttle materials through space. These methods promise to reduce travel time and fuel consumption, making the return of mined resources economically viable. As these technologies mature, they will significantly enhance our ability to engage in large-scale space mining operations. Moreover, the burgeoning interest in public-private partnerships is accelerating the pace of innovation. Companies and governments are working together to develop shared infrastructure, such as spaceports and transportation vehicles, that will support a burgeoning space economy. The shared investment in technological development and infrastructure not only spreads the financial risk but also accelerates the pace at which these innovations are brought to fruition. As we look to the future, the trends and innovations currently unfolding are setting the stage for a new chapter in human history, one where space mining becomes a cornerstone of our economic and technological growth. The industry is on the cusp of moving from concept to reality, driven by relentless human ingenuity and collaboration. The potential benefits are immense, promising not only economic prosperity, but also new opportunities for scientific discovery and exploration. As we continue to innovate, the dream of tapping into the vast resources of space transforms from a distant vision into an achievable reality, bringing with it a new age of exploration and sustainability for humanity. To truly understand the exciting potential of autonomous space mining, we can turn our attention to some pioneering projects and case studies that are laying the groundwork for this industry. These real-world examples illustrate not only the practical steps being taken right now, but also highlight the innovations and collaborations driving this field forward. One of the most notable initiatives is NASA's Artemis program, which aims to return humans to the Moon and establish sustainable exploration by the end of this decade. A significant part of Artemis is the Artemis Base Camp, envisioned as a long-term lunar surface presence. A key component of this base camp is the utilization of local resources, known as in situ resource utilization. NASA is working with partners to develop technologies that can extract and process lunar ice into water, oxygen, and even hydrogen fuel. These resources are crucial for crafting a sustainable presence on the Moon and supporting future missions to Mars and beyond. The testing of autonomous mining robots capable of performing these extraction tasks is central to the program's success, showcasing the practical implementation of space mining. Moving from public endeavors to the private sector, the ambitious plans of companies like SpaceX and Blue Origin also illuminate the potential for autonomous mining. SpaceX, under the leadership of Elon Musk, has primarily focused on developing the Starship, a fully reusable spacecraft that aims to make interplanetary transport affordable. While SpaceX has not explicitly outlined plans for mining operations, their advancements in transport technology are essential for any large-scale infrastructure needed for mining operations on the Moon or asteroids. On the other hand, Blue Origin, founded by Jeff Bezos, has made more direct strides toward resource utilization in space. Blue Origin's Blue Moon mission outlines a vision for lunar resource extraction that includes transporting equipment needed for mining operations. They are actively working on technologies that would allow for the extraction and processing of lunar materials to support lunar bases, aiming for a future where space is a self-sustaining environment. Their focus on creating a robust infrastructure for future space economies underscores the importance of resource extraction in long-term space exploration strategies. Additionally, companies like Astrobotic Technology and iSpace are making headlines with their efforts to develop lunar landers and rovers. These spacecraft and robotic explorers are designed to carry payloads, including the critical technology needed for mining operations. Astrobotic is set to deliver NASA's first payloads to the Moon under the Commercial Lunar Payload Services program, which includes tools for prospecting lunar resources. Similarly, iSpace, a Japanese venture, is aiming to transport payloads to the Moon with the goal of developing a lunar economy that includes mining as a core activity. Moreover, the European Space Agency is exploring concepts for mining in collaboration with companies like Ariane Group. They are investigating the potential of harvesting lunar regolith to extract oxygen and metals, focusing on sustainable methods that minimize environmental impact. These examples highlight a multifaceted and collaborative approach to space mining. They demonstrate how leveraging expertise from both government agencies and private firms can accelerate the development of technologies and infrastructures necessary for mining in space. As these projects progress, they not only pave the way for future resource extraction, but also stimulate advances in robotics, AI, and sustainable technologies that could benefit industries on Earth. In conclusion, these case studies showcase the practical steps being taken to turn the dream of autonomous space mining into reality. By examining the collaborative efforts and innovative strategies at play, we gain a clearer picture of how humanity is poised to extend its reach beyond Earth, opening new frontiers for exploration and economic growth. As these projects evolve, they will undoubtedly inspire further advancements and partnerships that could redefine our future in space. As we wrap up our journey through the fascinating world of autonomous mining robots, it's evident that we are standing on the cusp of a groundbreaking era in space exploration and resource extraction. These robots are not merely machines, they represent a beacon of what human ingenuity can achieve when combined with cutting-edge technology and a vision for the future. The developments in autonomous mining underscore a significant shift in our approach to resource management, one that transcends terrestrial limitations and looks towards the infinite possibilities of space. The potential impact of autonomous mining robots is profound and far-reaching. They promise to open up new avenues for scientific research by allowing us to access and analyze materials from the Moon, asteroids, and potentially even Mars. These resources hold the key to unlocking the mysteries of our solar system's formation and evolution, providing insights that could fundamentally alter our understanding of the cosmos. Imagine the discoveries that await as these robots bring back samples that were once mere points of distant curiosity. From an industrial perspective, the implications are equally significant. By tapping into the vast reservoirs of rare earth elements and other valuable resources found in space, we could alleviate the mounting pressure on Earth's limited supplies. This shift could lead to a more sustainable approach to high-tech manufacturing, supporting green technologies and promoting a circular economy. Moreover, the development and deployment of these mining robots could spur economic growth and create new jobs in emerging industries focused on space exploration and resource utilization. Beyond science and industry, the deployment of autonomous mining robots is fostering unprecedented international cooperation. As nations and companies work together to develop shared technologies and frameworks, we are witnessing the birth of a new global partnership model. This collaboration is vital not only for the practical success of mining ventures, but also for ensuring that space exploration remains a peaceful and equitable endeavor. These efforts remind us that while the resources are extraordinary, the human spirit of cooperation and shared ambition is what truly propels us forward. Yet, with these opportunities come responsibilities. As stewards of both Earth and space, we must ensure that our mining efforts are conducted sustainably and ethically. The quest for resources must not come at the expense of celestial environments or the integrity of scientific research. Establishing robust international agreements and sustainable practices is crucial to preserving space as a realm of opportunity and wonder for future generations. As we conclude this exploration into the potential of autonomous mining robots, we encourage you to keep an eye on these exciting developments. The technologies and alliances formed today are bound to play a defining role in shaping our future, one where space is not just a frontier to explore, but a landscape to inhabit responsibly. The journey is far from over, and the next chapters promise to be even more thrilling. Thank you for joining us on this journey. We invite you to share your thoughts and insights on this topic in the comments below. If you found this exploration enlightening, don't forget to like and subscribe to stay updated with our latest content. Together, let's continue to look to the stars, inspired by the boundless potential that lies ahead.